right? The g-force, if you go faster, what happens to the g-force? Yeah, definitely if you go faster around the same corner, the g-force increases. And apparently it's a square, right? So if you double your speed, you actually will quadruple the g-force, which is why you see all those tire tracks going like straight off the edges of corners. You ever see those? It's like, wow, I wonder what happened there, right? You know? Okay. How about like, how about that road? You're going on Highway 26 and you want to go to Cannon Beach, right? So you take that little ramp that takes you to 101 South, yes? You know what I'm talking about? And it says 15 miles per hour, but you get on it and you're like, well, I can go a lot faster on this. I can go 45, yeah? What does it do, though? What happens to the radius of that curve?
It shrinks.
Yeah, the radius goes from, this is a big wide curve to, what did the engineers think? They're like, oh crap, let's just turn it right here, right? So it turns from this big wide curve to like this tiny little thing, right? And you really do have to go like 15 miles an hour, 20, your wheels are singing, right? And then you could see all those like rubber marks up the little barrier that show that people like actually didn't believe that and like went off, yes? Okay, so as you decrease R, what happens to the g-force? Yeah, it goes up by a lot, right? And then the other thing I can do to convince us that this is the right formula is we can put units in there, right? So let's solve a problem, right? Let's have a car go 24 meters per second around an 80 meter radius corner, right? And then the question, then let's have it be a 1,200 kilogram car, right? So there's this car going around this corner. So all curves have a radius of curvature. This one apparently has a radius of curvature of 80 meters, right? 1,200, they're seeing it from the top, you know, 24 meters per second. So the first step is to just find the acceleration, right? So the acceleration is v squared over r. So that's 24 squared, and that's meters per second, right? And then divided by 80 meters. And then check out what the units do. Check out the units. In the numerator, you're going to have meters squared per second squared, right? Divided by meters, right? It's just meters per second squared. Are those the units of acceleration?
No.
I'm thinking they are, yeah. So 24 squared divided by 80. And this ends up being 7.2 meters per second squared. So the units all work out. It is meters per second squared. This is at least hopeful, right? We know that the formula is not necessarily wrong, but you know, there it is, right? Okay. And then to figure out the force needed, I'm just going to use F equals ma, right? Now this is lateral force. This force here is lateral force, so it's force that's toward the center of the curve, right? And so that's 1,200 kilograms. And the good news is we don't need to reinvent Newton's second law. It's the same second law, right? 7.2. So let's see, times 1,200. So this is 8640 newtons. Ta-da. Right? And then finally, the last thing I will do, are there any people here that read car magazines? Yeah, there we go. Okay, so we got some car fanatics. Keenan would be one of these people, my son, right? Let's talk about this. This acceleration, the centripetal acceleration, is also known as lateral. So in car magazines, they'll talk about the lateral G's that a car can pull. This is a specification. So the 0 to 60 is your linear acceleration, yes? Sports cars need to be able to accelerate fast forward or they're no fun, right? They also need to be able to go around corners, and what they do is they talk about the lateral G's. This is what centripetal acceleration is a lateral acceleration. Lateral just means to the side, right? So this, in G's, if I wanted to figure this out in G's, I'd go 7.2 divided by 9.81. So 7.2 divided by, that's about 0.73 G's. Okay, is that a lot of G's?
No.
Well, 1 G means that you're basically, there's as much force to the side of you as there is straight down, right? So that's a ton of G's. This is actually quite a bit. Your average Econobox is going to lose control at about 0.8 G's. The suspension can go up to about 0.8 G's, and that's pretty good. I know that the old Volkswagen Beetles weren't that good, so if you got going around a corner at about 0.6 G, something very undesirable happened with the suspension. A good sports car, a really good sports car with good tires on a clean road is going to, for reasons that we don't understand now because we don't study friction, like coefficients of friction, but it will approach 1g. So 1g is sort of like the limit, and then you can go above that if you somehow hold yourself down to the road with a force bigger than your weight. Yeah? If you can somehow glue yourself to the road. And so I think one Indianapolis 500, somebody actually made a car that sucked the air out from under the car and made a partial vacuum under the car so the atmosphere pressed it against the road. And boy, if you can hold yourself down to the road harder than everyone else, you can go around the corners faster. Yeah, it was the winged keel of the race. I mean, they won by laps and laps and laps. Yeah? Okay. Nowadays they don't, I think you can't suck the air out. You can't have a separate motor that sucks the air out from under the car and glues it to the road. But they do have like ground effects which reduce the air pressure under the car. They also have wings. Like the cars that race in the Indianapolis at something like 200 miles an hour, 100 miles an hour, some speed, they can actually drive on the ceiling. Yeah. There's more force generated by the air down on those cars than by gravity. Isn't that wild? Yeah. So if you could get the engine to oil itself, right? If you could get the oiler to work on the engine upside down, right? Then you could drive an Indianapolis car on the ceiling. It would have enough. If you could just design a curve that would like put them up on the wall first and then gradually turn them upside down, they could do that. The only problem is that a real car, the oil would no longer go to the right place and the pump wouldn't pick it up and it would stop like in about 100 yards. It would go and stop, right? Think about how about airplane engines? How hard is it to oil an airplane engine? Yeah, a sustained dive or a roll or something like that, right? Can put the oil in places that you don't expect. So yeah, engineers have to be very clever about how those. Why are we talking about that? Okay, good. Yes. All right, we've solved that one. And then the final thing is, go for it. The final thing is that with this acceleration, which way is this acceleration? Which way is this guy accelerating as he goes around in the circle? Are they accelerating toward the middle or toward the outside? Everybody says to the outside. So let's consult the magic crystal. Okay. O accelerometer. Which way do you point? Well, remember this float. Which way does it point? Does it point opposite the direction of the acceleration or in the direction? Opposite. Let's try it. Let's remember. I'm going to accelerate that way. Which way will it go? Doesn't it go that way? Yeah. So this thing, there's no tricks about it. Well, it's sort of tricky, right? Okay. The water actually sloshes to the back of the jar, pushes the float forward. Okay. So this thing will point in the direction of the acceleration. So now, let us take this and rotate it. Yes? Are we ready? Which way is it going to go?
It's going to go towards
inward or outward?
Actually, it's going to go.
Wait, which way are you rotating?
It's going to go inward.
It's going to go inward.
Let's just take a vote. How many say it's going to go inward? Raise your hand. How many say it's going to go outward? Raise your hand.
Evens.
All right, here we go. It is, by the way, going to go inward or outward, right? Okay. It's not like the cause of the Civil War. We can disagree about that.
It goes inward.
Inward.
Which way is it going?
Inward.
Inward. There we go.
How's your head feeling?
All right. Here we go. Yeah. So remember that it's always that way. The reason why you thought that the acceleration was outward was that of course, objects feel like they are flung to the outside. Yes? My older siblings used to do this. I was the youngest, right? They would do something they would call it centrifugal force, right? And they would say, centrifugal force, every time we went around a corner, and they would just jam me to the outside of the curve. Yes? Okay? You always feel thrown opposite the direction you're accelerating. Think about it. If I accelerate that way, which way do I feel thrown? I feel thrown backwards, but I'm really accelerating that way. So if you feel thrown to the outside of the curve, you're really accelerating inward, right? Because that's the way your direction's changing. Not your speed, but your direction. Okay? So a constant linear acceleration is like this. It's like, right, going faster and faster. A constant centripetal acceleration is like this. You're moving in a perfect circle at a constant speed. You put the cruise control on the car, you go out in the middle of the Great Salt Lake on the flats, the salt flats, not the lake part, and you turn the steering wheel and duct tape it at a certain angle, put the cruise control on, and sit back and read a book. And your car's sitting there going around and around and around. That is a uniform centripetal acceleration. And then finally, the word centripetal just means toward the center. So centripetal is a word that means toward the center. Now, it really doesn't help you because you didn't know what it meant before this. And